Chapter 9, Section 6, Solving Right Triangles. To solve a right triangle, remember that all right triangles are going to have a right angle, two acute angles, one hypotenuse, and two legs. To solve a right triangle, you have to find the measure of all of these parts. So you're going to have three different angle measures. One of them is always going to be 90 degrees of right angle. And then you're going to have three different side lengths. So far in Chapter 9, we've talked about the Pythagorean theorem, and we've also talked about our trigonometric ratios in the last lesson. Those two things are going to help us solve a right triangle. If you know the sine, cosine, or tangent of an acute angle, you can use a calculator to find the measure of the angle. So far, we've been able to use our trig ratios to find the lengths of sides, but they can also be used to find the measure of missing angles. For an acute angle A, if the sine of A equals x, then the inverse sine of x, notice that I have sine to the negative first power that's read as inverse sine, is going to be equal to the measure of angle A. If the cosine of A is x, then the inverse cosine of x is going to equal the measure of angle A. And then if the tangent of A equals x, then the inverse tangent of x equals the measure of angle A. If you look at your calculator, you need a scientific calculator that does have sine, cosine, and tangent. I think most calculators, and there might be a few exceptions out there, but most calculators that are scientific and have the sine, cosine, and tangent buttons, if you click the second sine button, you should get inverse sine, so you should get sine to the negative first power. If you click the second cosine button, again, you're going to get inverse cosine, and then if you click the inverse tangent button, then you're going to end up with the second tangent button, then you'll end up with the inverse tangent. So make sure that if you just want to pause this video and grab your calculator really quickly, I believe iPhones, if you tilt them so that they are horizontally facing, then you should be able to see sine, cosine, and tangent trig ratios, and I believe that's also a second button that you can click second sine, second cosine, or second tangent to get the inverse of each. On your calculator, I want you to go ahead and you can pause this video to give you a little bit of time to do it, but on your calculator, I want you to go ahead and do the following. I want you to first find the sine of 85. So in your calculator, make sure you're in degrees and just find sine of 85. Then what I want you to do is I want you to take that number and I want you to find the inverse sine. So I want you to take that number. You can use, on your calculator, you can use the answer button. So you can do second sine and then you could do second wherever your answer is. And what answer does is it goes ahead and it plugs in the last function that you had done. In this case, it would have been a trig ratio. So go ahead and find sine of 85, and if you want to, you could also just write that number down. The more you round, the further off it's going to be, though, so you want to be as exact as you can be. So take sine of 85, and then whatever your answer is, I want you to take that number and take the inverse sine of that. I want you to do the same thing with cosine and tangent, and then you can continue on to this video. If you noticed, it says what happened. If you used your calculator correctly and you got you entered everything correctly, then anytime you took the sine of 85 and then you took the inverse sine of that number, you should have ended up back with 85 degrees on all three of those from the last slide. I want you to go ahead and take a minute and pause this video, and you can even try a couple, but choose your own acute angle measure and see if that works. And then my second question is, does it work for an obtuse angle measure? So go ahead, if you're watching this, go ahead and pause your video. Take some time to kind of mess with your calculator and see if that's going to be true for all acute angles, and then I want you to test if it is true for an obtuse angle measure. Once you've done that, you should be able to see that, again, if you're using your calculator correctly, it is always going to work for the acute angle measures. So taking the sine of 35 and then taking the inverse sine of whatever you get for sine of 35 is you're always going to end up with 35, or whatever acute angle you chose to use. It does not always work for obtuse angle measures. It might happen every once in a while that it does work out, but it is not something, it only works for acute angles, not all obtuse angles. The first example says, solve the right triangle, round decimals to the nearest tenth. Something that I want to point out to you is that there are several different ways to do this problem. You could use all trig ratios. You could, there's lots of different ways that you could do it. So I'm going to show you one way to do it. We might even do a different way in class sometimes, but just know that this is definitely not one of those situations. Now, whichever way you choose to do it, you should end up with the same answers as I'm getting, but you can get to it a totally different way. When it says solve the right triangle, I know that I have a right angle. They gave me two side lengths. So what I need to do to solve this right triangle is I need to find the missing side length, which is B, and then I also need to find the measure of angle A and the measure of angle C. The first thing I'm going to do is go ahead and find the measure of side B. To do that, I'm going to use the Pythagorean theorem. In this case, B is my hypotenuse. 8 and 10 are my legs, so I would say 8 squared plus 10 squared equals B squared. Well, 8 squared is 64 and 10 squared is 100, so 64 plus 100 equals B squared. 64 plus 100 is 164. Take the square root of both sides, and because it did ask me to round decimals to the nearest tenth, I'm going to go ahead and take the square root of 164, just plug it into your calculator, and you get about 12.8 for B. So now I know all three side lengths. Now I need to use a trig ratio to find one or both of the angle measures. Something that a little pointer that I like to share is that I would prefer you to go back and when you're using trig ratios, I would like you to use the two side lengths that they gave you in the problem. So notice we have AB is 8 and BC is 10. The reason why I like to do that is because could you have made a mistake to get 12.8 for B? Absolutely. And so if you use 12.8 and it was wrong, I know that it's right, but if it was wrong, then you would automatically get the next two problems wrong, or the two angle measures wrong. So always, if you can, use the information that they give you every time so that you can so that you at least have a chance to get the correct answer if even if you got the first part wrong. So this is where there are lots of different ways that you could go about doing this. I believe I'm going to find the measure of angle A using 8 and 10, which would be the opposite and the adjacent sides. So I'm going to say that the tangent of A equals 10 over 8. Well, 10 over 8 is 1.25. This is where the inverse tangent is going to come in handy now. So the tangent of angle A is 1.25. So to find the measure of angle A, I'm going to take the inverse tangent of both sides. So the inverse tangent of 1.25 is going to equal the measure of angle A. In your calculator, you would enter second tangent to get inverse tangent, and then just plug in 1.25, and you should get 51.3 degrees. Now that I have a 51.3 degree angle and I know that I have a right angle, I'm going to take the 90 and the 51 and I can add them together, plus angle C would equal 180 degrees. Go ahead and add 51.3 plus 90 and subtract that from 180, and you get C would equal 38.7 degrees. So now I have all three angle measures. Angle B is 90 degrees, that's given to us. Angle A is 51.3 degrees. Angle C is 38.7 degrees. I know that the missing side, the hypotenuse is 12.8. So I have solved this right triangle. In the next example, it says to solve the right triangle, round decimals to the nearest tenth. If you notice, in this case, I have a right triangle at angle T. They tell me that angle R is 20 degrees, and I can use the third angles theorem to say that the measure of angle S would be 70. So I said 20 degrees plus 90 degrees plus angle S would equal 180. Go ahead and combine 20 plus 90 is 110. Subtract that from both sides and you get S equals 70 degrees. Now I'm going to be able to use trig ratios to find the missing side lengths R and S. You can do these in whichever order you want to. I went ahead and I chose to solve for R first. I said that the sine of 20 degrees is the opposite, which is R, over the hypotenuse, which is 15. Multiply both sides by 15, so you would have 15 times the sine of 20 equals R, which would give you 5.1 for R. From this point, you have two different options here. Now that I know two side lengths of the triangle, I could use the Pythagorean theorem, or you can use another trig ratio. It doesn't matter either way. Sometimes if you use the Pythagorean theorem, if you've already rounded once, if you've rounded the 5.1, you're going to be a little bit off on your answer. However, for my class at least, if you're watching this and you're not in my class, then do whatever your teacher tells you to do. But for my class at least, it's not going to make a big enough difference in any of our problems for me to count a problem wrong, depending on what you did. For this example, I just used another trig ratio since they're new to us, and I actually used 70 degrees to find S. So I said that the sine of 70 degrees is opposite, which for angle S, or the 70-degree angle, which would be S, over hypotenuse, which is 15. Again, I need to multiply both sides by 15, so 15 times the sine of 70 equals S. So S equals 14.1. And again, if you use the Pythagorean theorem, you would get, I believe in this case, you actually do get 14.1, so it's not that big of a deal. This next example says, during a flight, a hot air balloon is observed by two persons standing at points A and B as illustrated in the diagram. The angle of elevation of point A is 28 degrees, which I've already marked on the picture. Point A is 1.8 miles from the balloon as measured along the ground. A says, what is the height h of the balloon? Notice I have a 28-degree angle at angle A, and I know that the distance from the hot air balloon to the person at A is 1.8 miles. So what I can do is I can use a trig ratio. I want to know the side opposite my 28-degree angle, and I know the side adjacent is 1.8. So what I'm going to do is I can use the tangent of 28 equals opposite, which is h, over 1.8, which is the adjacent. Multiply both sides by 1.8, and you get 1.8 times the tangent of 28 equals h. Plug it into your calculator, make sure you're in degrees still, and you get h equals about 0.96. B says point B is 2.8 miles from point A. Find the angle of elevation of point B. Notice before I even read that, I already had it marked on my diagram. But in the, if the point from A to the hot air balloon is 1.8 miles, and we know that A and B are 2 miles apart, then 2.8 miles apart. 2.8 minus 1.8 leaves 1 mile to be between the height of the balloon and the point B. Now I want to find the angle B. I know that the h is 0.96, so I know the side opposite and I know the side adjacent. So what I'm going to say is the tangent of B is opposite, which is the height, which is 0.96, over 1, which is adjacent. Well, 0.96 times 1, or divided by 1, is just 0.96. I need to take the inverse tangent of both sides, and B is going to be the inverse tangent of 0.96. Plug that into your calculator. Remember, it would be second tangent of 0.96, and when you do that, you're going to get that angle B is about 43.8 degrees. Today's assignment is on page 570. It's numbers 12 through 26 even.